Hello, everybody. Welcome to another Bitshala Review Club session. And today we are going to discuss the part two of the functional test for the new thing that is coming into Bitcoin Core, BIP324, and all about like encrypting the P2P messages. In the last club, we talked about the basic functional test framework and how does the functional test framework work. So if you haven't seen that, do check that video out. And in this we are going to deep dive into BIP324 technicalities, right? So without further ado, Stratosphere, the stage is yours.
Okay. So, it's a continuation of our last peer review club. There we examined how the test framework actually works. And today we're going to look into how we can add V2 P2P support for it. So, anyone wants to give a quick summary of what the PR actually does?
Okay, so like I haven't like dived deeper into it, but from the overall look of it, it seems like it's trying to create those encrypted. It's trying to mostly like trying to simulate the handshake sessions between that is the difference between the V1 and V2 of protocol messagings and checking like whether the nodes are responding correctly or not. Um, but I might be missing something.
Yeah. So, like to talk in V2, like we need to do that initial Diffie-Hellman handshake version, the
Right.
advanced form of that. So this PR adds support for that. And once we have done the handshake, both uh, like the test node and the Python P2P interface,
Mm-hmm.
uh, both of them will have the same shared secrets, and they will have both keys to both encrypt and decrypt messages.
Right.
And PR also adds support uh, for talking in that new message format with encrypted connections.
Makes
So the
sense. Yes.
message packets are now encrypted, and this is only for test node and a P2P interface kind of communication, not for between two test nodes, because test nodes are already Bitcoin D processes, and they
Right.
have support for the J24.
Right.
And
So here we wanna like
oh yeah,
one question I had is like why we are not like trying to test the handshake between test node, because the test node already have that code, right? So they can like handshake v2. So is there no
yeah,
way for like for two test nodes to do that and try to see like if it's working or not
yeah. Those
instead of
tests
like
are
P2P interface? Yeah.
those tests are already done. Like
Okay.
they had it in the initial, like there's a file just for doing the test node interactions. Like they've already
Oh,
written the
okay.
test for it.
Okay. That makes sense. Okay. Yeah.
So I think this adds more control, right? So what if like within the handshakes, if the second client drops out and things like that, right?
Yeah, we
Mm.
can add. Yeah, and there is decoy packets. Like all those things are optional. Like we don't like the Bitcoin D has support for sending decoy packets, but it doesn't always send it. So you can test very specific stuff like that.
Right. So you wanna like create all these kind of edge cases and sometimes even like abort or malice behaviors. And
Yeah,
okay, for that you need like the P2P interface. Makes sense.
yeah. And V26 release notes with BIP324 support.
Wow. Congrats. When did this came?
I think yesterday, December
Oh,
6th.
nice. Okay, December 6th. Yeah, it was yesterday. Okay,
Yeah,
so it's in version 26 or
yeah,
version
yeah,
26, right? Nice. So, and it has a
Do they
config
have?
parameter,
yeah, default of parameter.
a default of V2 transport, and you can turn that on. I'm excited to try that on my node. Yes, nice. Yeah, Emil,
Do
go
they
ahead.
have? Yeah, contributors names.
Uh, oh yeah, they
It'll be too.
do.
It should be too big. No, it's okay. Yeah.
Yeah.
So yeah, I tried this thing with. I mean, without taking the release build, I just took master, but there is no other way to node I could find. So
That's
if
yeah.
you do a V2 node.
Yeah, we will be the first two peers. Yes, yes,
8 hours.
definitely.
Yeah, I think 8 is running something now just to help, uh, like for people to test it.
Right,
Like
right.
I
Yeah,
saw it.
I guess like some developers would be running it. Yeah, makes sense because yeah, people will be trying to test it out.
Yeah, I don't know. You'll have to. 8 was it fine? I don't know. Oh, search. I don't know. I'll tell it to you later.
Okay, okay,
That's
cool. Yep.
okay. No, we're moving on.
Okay, let's move on.
Yeah. So what were we talking about?
We were talking about mostly about like what does this PR does, like specifically 24748, and we talked about like this PR is like doing the V2 handshake thing for P2P interface. So we wanna simulate all these kind of like malice and abort case situations and all the edge cases of the protocol. That's
Yeah.
also yeah.
Yeah. Yeah. So the first thing we need to it's kind of related to the questions. Like, and
Hmm.
the first thing I want to take a stab at is the initial V2 handshake, and that's also kind of a question. So we'll just go with
Right,
it.
right, right. So, yeah, so like describing the initial V2 handshake process, and I guess like it's kind of self-explanatory from the API, like it looks like from the function names. So, first you wanna do a initiation, and at the initiation stage, you wanna say all the details that you need to share with the other peer, like your public keys, and I'm curious what are the other details that actually get shared, and then the other peer will respond to their part of that details, and probably at that stage they are going to do some computation and come up with a shared secret, and then I think they will not like share the shared secret around because like they will generate locally and keep it there, right?
Yeah. Yeah. They won't share it. Only both of them should know it.
Mm-hmm. Makes sense. Okay. So yeah, I guess like this is like the protocol at least at the handshake stage, and
Yeah.
allocator Swift X is the public key X coordinate, and initiator garbage is like some extra data, so it's not identifiable as a public key X coordinate.
Yeah,
And
NPLS Swift X is not the X coordinates, just the alligator Swift encoding of the public key. So here the
oh,
initiator
okay,
has X and capital X. Here the responder has Y and capital Y.
right, okay, so what is X basically then?
It's just a public key. Like they just meant small x is private key and capital X is public key of
Oh,
initiator.
okay, 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 so it's not that X only public key thing, it's like a full public key, right?
Uh, it's not even a public key, it's the alligator Swift encoding of a public key.
It's the encoding of a public key. Okay, understood.
Oh, wait, what? Oh, so that's an actually ECDH is there.
Okay. And these are the
I mean, you
steps
can
of the
get
calculations.
because you can
Yeah,
get Y right from if it's odd or even and things like that. It will
yeah.
basically, yeah, yeah.
Yeah, so they use X-only stuff, but this capital X and capital Y just refer to public keys.
Okay. So capital Y means like just the responder's public key.
Yeah,
Okay. Okay. Cool.
yeah. Oh yeah, I wanted to draw this. Okay. Oh, oh, okay. I have to share my screen then. Can you see it?
Exactly. Yes, we can say it. Looks
Okay, you can
fancy.
see it, right? Yeah. I
Nice.
hope it gets recorded.
Yeah, yeah, it's
Yeah.
getting recorded. It is getting recorded.
Yeah. So there are two nodes. Like we'll just look through this because then these other two functions, like the functions in the Python code, like you'll need to know what are actually being sent and received
Mm-hmm.
in the handshake.
Right.
So we are just going to look at this. So there's the node, two nodes, and yeah, they need to talk. So like it's Diffie-Hellman key exchange basically.
Mm-hmm.
So if this node has uh, like it like small like private key and public key pair, and the other
Right.
node has private key and public key pair. So during Diffie-Hellman key exchange, what you usually do is this node will send its public key to the other node,
Mm-hmm.
and the other node will send its public key to the other node.
Right.
So now this node will have its private key and the other node's public key,
Right.
and this other node will have its private key and the other public key. And
Right.
we know that this public key is the private key times the generator,
Right.
and this one is the private key times the generator. And so you see that
They both end
what
up with the same
these two
number.
things, yeah, it's the same shared secret.
Right.
So that's kind of what we want to do. Uh, but we modify it so that we don't just send the public key as such. We send the L-Swift encoding of it,
Mm-hmm.
because public keys are elliptic curve points, and they will always satisfy the elliptic curve equation,
Right.
right?
Right.
And also, if you do some kind of traffic analysis, if you have if you just observe random bytes over the wire, uh, and if you test for elliptic curve points, only 50% of these uh, bytes would be actual valid elliptic curve points.
Mm-hmm. Okay, I
But
didn't
then
get
if
that.
you're
Like
only sending public,
if you're sending random bytes, around 50% of them will be valid elliptic curve points.
yeah. So
Okay, how is that 50% coming up? It's a side topic though, but anyway.
yeah, it's like a statistical analysis. So if you are uh, I don't know, like imagine like we are sending uh, X only public keys, 32
Mm-hmm.
bytes,
Mm-hmm.
right? So if you're actually sending public keys, all of them will be valid public keys.
Mm-hmm.
If we are actually sending public keys.
Right.
So an attacker or an eavesdropper who is actually uh, looking at these connections, he will observe each of these 32 bytes, 32 bytes, 32 bytes, and he will see that with 100% accuracy, all of
Hmm.
them are valid public key points. So he will know that we are sending public keys on the wire.
Right.
But supposing it's a random bytes being sent, not public keys, someone is sending random bytes, then the probability of each of these random points being valid public keys, it's only 50%.
Okay.
So it's possible that this 32 bytes is a valid public key, but this is not a valid public key. Next one is not a valid public key. So it's not necessary that they're all valid public keys. So there's only a 50% accuracy that uh, if it's on a random byte stream, that stuff are valid public keys.
Right. Okay, makes
And
sense.
how alligator swift prevents this is like any 64 bytes, they are valid. Alligator swift is actually 64 bytes encoding.
Mm-hmm.
So here we were just talking about 32 bytes. So imagine it's just 64 bytes. So all 64 bytes, they are valid public keys. So it doesn't matter if an attacker is eavesdropping. He observes 64 bytes, but he can't say for sure whether, like, he won't know if it's a public key or not, because they're
Okay.
all valid public.
Okay. Okay. So like if you I mean, like, so is it happens like, so for each public key, you do a alligator swift and you transform that public key into a 64 byte stream.
Yeah.
And then do you send that stream only, or like you send other streams like to confuse the attacker?
We sent only this stream. Like,
Okay. Okay.
we're only talking about alligator swift, so we send this stream.
Hmm.
But this looks random. So an
This looks
attacker
random. This
wouldn't be
doesn't look like a
able to,
public key. Okay.
yes. So attacker would not be able to do any traffic analysis on it.
Mm-hmm. Okay. So it can be any 64 bytes stream, and only another node will get to know that it's a public key.
Yeah, any 64-byte encoding is a valid public key. There's no, like, you can't get numbers like 100%, 50%. They all look random and they all could be like valid public keys.
Okay.
There's like maybe a clearer explanation. I don't know, maybe this wording will make sense to you. Like, I'm just reading this. Can you see the screen?
Yes.
We can only
Yeah.
see the drawing.
No, you have to select her screen. Like there is two screens going on.
Oh, okay, okay.
Yeah. Okay, so in my recording, I think, yeah. So it's written here. Sometimes it's desirable to be able to send elliptic curve public keys as uniform byte streams. In particular, a Diffie-Hellman key exchange requires sending a group element in both directions, which for elliptic curve based variants implies sending a curve point. As the coordinates of such points satisfy the curve equation, this results in a detectable relation between the sent bytes if those coordinates are sent naively. Even if just the x-coordinates of the points are sent, the knowledge that only 50% of the x-coordinates have corresponding points in the curve means that an attacker who observes many connections can distinguish these from random. The probability that 30 randomly observed transmission would always be valid x-coordinates is less than 1 in a billion.
Okay.
So it's like a traffic analysis kind of thing, which would happen if you just send public keys over the wire.
Understood.
Different language.
Okay. Understood. Okay. So back to the drawing again.
Yeah. So we don't send just alligators, like we don't just send the public keys, we send the alligator swift encoding form of the public key. And also we need to send the transport version.
Right.
For any protocol, like, so that both of them will talk at a protocol, like will talk at a protocol which both of them understand. Right? So right now we have encrypted P2P support, that's V2. Suppose in future authentication or something is added, then both of them would, like if like node 1 supports encryption and doesn't support authentication, and the other node supports encryption and authentication, we should only talk in encryption protocol. Like we should talk in the least supported protocol. So for that, we have transport version exchange so that we can upgrade.
Why would a node not have authentication and encryption only? Like, why is it not enforced in code by default?
Authentication and
Encryption.
like we have authentication of, yeah, we have authentication and encryption for a message which is being sent, but not for the connection as whole. Like, because like there are two meanings for authentication, right? Like one is we want the network message being sent to be authenticated, and the other is we want to authenticate the actual connection.
I mean, like it's kind of like identity in the sense like the peer knows like I'm talking to this guy, and if he comes back
Yeah,
again, he will be able to identify, okay, that's the previous guy. Okay.
yeah. So when I mentioned authentication, I meant the second meaning where uh, there is authentic, like the example you mentioned.
Right. Makes sense.
So this
Okay.
is not there in, like this is optional. Like we don't want to make a concept of identities in a P2P network unless it's
Hmm.
for some very specific scenarios,
Hmm.
like it
Hmm.
really trust the person or your own nodes. So
Right.
that's kept in future.
Right.
So that's
Okay.
like a future. Yeah. So just to provide the path, we have a transport version which is being sent. And right now it's an empty packet which is being sent. Like there's nothing inside.
Okay. So it's like
So
a zero
yeah.
byte stream, basically.
Uh, so the content is just empty byte stream, but then when you put it into the network message structure, it will get more bytes.
Okay.
Uh, like this is the V2 P2P message format. So it's 3
Right.
bytes length, 1 byte header, content, and 16 byte max. So this contents will be empty. So this will be 0 bytes, but then you will still get the bytes from length, header, and mat. So 3
Hmm.
plus 1 plus 6. So the packet will be 20 bytes long, even though the contents are empty.
Okay. Okay. Makes sense.
Yeah. So yeah. So but then this one had a detectable pattern, right? Like 64 bytes. Transport version is 20 bytes. So we don't do that. We want to make the byte stream shapeable.
Mm-hmm.
So for that, we send this initiator garbage, responder garbage, those kind of stuff.
Hmm. Right. So
Uh,
like the length,
so
like you cannot identify messages via length also. Like there is no fixed length message anymore.
yeah, there's no fixed length message anymore. So garbage is also being sent by one node, and to know when the garbage terminates, a terminator will also be sent.
Okay.
And the other thing also will send garbage and will also send terminator. This terminator will only be known by this node and nobody else, because it's derived from this shared secret.
Ah, okay.
So nobody else will be able to know when the garbage actually terminates except these two nodes.
Hmm. Okay. And not necessarily the garbage will, like the terminator will be at the end of the garbage stream. It can be, I mean, the middle of the garbage stream or no?
Terminator means the garbage terminates, so it has to be at the end of
At the
the
end of the
garbage stream.
garbage stream. Okay.
The garbage can be up to a maximum of 4095 bytes. So
Mm-hmm.
maybe you could send just 20 bytes garbage followed by the terminator, or maybe you could send 100 bytes garbage followed by the terminator. It's all shapeable.
Right. And who will
And
decide
for
that? Like the node will decide it randomly?
yeah, from the randomness
Okay.
in the
Okay.
node,
Makes sense.
yeah, that's some algorithm.
Okay, cool. Um, yeah, let's move ahead from here then.
Yeah, yeah. So those are the stuff we saw. Now, like if you look at this diagram, you can see like the initiator will send the alligator swift and the garbage, and so the initiator will have its private key and public key.
Right.
Can you hear me?
Yes, yes, we
Yeah.
can.
Okay. Yeah. And the initiator will send the public key and lots of garbage, and the responder will generate its private key and public key. And now you can see that ECDH is possible now because you have your private key and you have the initiator's public key.
Right. Yeah.
So you can derive the shared secret. If you derive the shared secret, it means like you can have the keys to encrypt, decrypt, and you can send uh, messages in this V2 format.
Right.
And this is a function which will initiate instantiate all the keys and the terminator.
Right.
And then this responder will respond back with the public key, lots of garbage, whenever the garbage ends the terminator. And it can now send encrypted packets, right? Because it has the shared secret. And the encrypted packet will contain the transport version, which is empty for now.
Okay.
And it will also authenticate the garbage. So AADs, like it doesn't make sense to encrypt garbage, right? Because it's just random bytes. Why waste computation trying to decrypt garbage when it's just
Right.
garbage? But you also want to make sure that the data hasn't been tampered with. So you can pass it into this construct. So this is actually an authenticated encryption algorithm. It combines both authentication and encryption. So it will encrypt this contents of this, that is this responder transport version, and it will authenticate the responder transport version, and also the garbage. So if someone flips garbage, we will
This will complain like
fail.
something is not matching up. Okay.
Yeah, this will fail and disconnect. So even if that garbage has flipped, or like someone changes something, you will know, and the connection will disconnect.
Right. Okay. So, like, even if it's garbage, we want to ensure that it's the right garbage, but we don't
Yeah.
want to necessarily decrypt it.
Yeah, we don't want to decrypt it.
Makes sense. Okay.
And then, so now the initiator has got the public key. So it can do ECDH, it can get all the shared secret, derive all the keys to encrypt, decrypt. It can also find out the garbage terminator, and it can sense the terminator and also whatever transport version it supports. And it will also authenticate its garbage.
Right. Makes sense.
Yeah. So that is the the initial V2 handshake. And if you look in the tests, yeah, it's basically just written code for doing that. Yeah, so like if you look at the, like you can, so like the code divides the handshake into, like the Python code divides, it's just an implementation thing. You can implement it however you want. This Python code like divides the handshake into 3 different steps. So there is different sequences if you're an initiator and if you're a responder. This happens because of inbound outbound connection difference.
Right.
Okay, we look at,
Okay.
yeah.
So here, like the initiator is using like initiate V2 handshake, and then it's going like complete handshake and then authenticate the handshake. And the responder is like for the initiating V2 handshake, the responder will go and say like respond for a V2 handshake, and then like it will get its data, and then it will complete the handshake, and then it will authenticate the handshake. What does it mean by authenticating the handshake?
Yeah, so yeah, we'll get there. Like we'll go first initiate, complete, authenticate. Authenticate handshake actually kind of has to do with this garbage like this thing I told you about. Like making sure that these decrypt correctly and that the garbage hasn't been tampered with.
Right, right. Okay. So it's like the authenticating, like all the data that was supposed to come has come.
Yeah, and hasn't been tampered with.
Makes sense.
So why isn't it part of complete handshake?
Yeah. Let's first look into what initiate V2 handshake, respond,
Yes,
complete,
yes.
and then we should ask again. Yeah, so initiate V2 handshake is basically just sending alligator, swift, and garbage. This first part, just sending alligator, swift, and garbage, is what initiate V2 handshake does. And interestingly, respond V2 handshake does the same thing. So you can see that respond V2 handshake will return self.generate key pair and garbage. Initiate v2 handshake also returns self.generate key pair and garbage. So both of them, like initiate v2 handshake does this and respond v2 handshake does this. The
I mean,
difference
they
is
are like the
that,
same thing, like for two different people, like who is going first and who is going second kind of situation.
yeah, exactly.
Right.
So yeah, so if you're going first, you can like directly send it. When the connection is established, just send alligator swift and garbage. When you're going second, uh, uh, in the BIP, they specify when you should respond back. Like you shouldn't wait for all the 64 bytes of the alligator swift to be received and then respond. Because if you get all the 64 bytes that's and then respond, an attacker could who is watching all your traffic patterns would be able to identify this pattern, like, oh, this person is responding only after 64 bytes, and that's like a detectable pattern, and we don't want that. So the BIP says that you should respond back when there is a mismatch happening from v1 prefix. V1 prefix is if this is what V1 prefix is just 16 bytes, which would be sent first if you were talking on V1 protocol. So you would send basically version message if you were on V1 protocol, right? Because that's the first message being exchanged. So if the initiator was talking on V1 protocol, they would send version message. So so basically, the only so what the responder does it will respond back with alligator swift bytes only when there is a mismatch from 16 bytes from uh, v1 prefix. Does that make sense?
A bit. I'm still a bit confused. So there is a v1 prefix, and the v1 prefix is 16 byte, and it denotes what?
The
Can
version,
you
I
see my
think, right?
Yeah, can you see my
Yes.
screen?
Yeah, we can see your drawing
Yeah,
board.
yeah. So imagine this is the initiator. So initiator will always send 64 bytes lswift, right? If it is
Okay.
a v2 connection. If it was a V1 connection, what would this initiator would send version message,
Right.
and this version message has a pre-specified format, which is 4 bytes network magic, then 12 bytes, which is version V in plain text, version, right?
Right. Yes.
So so this person here doesn't know whether they are whether the bytes they received are v2 bytes or v1 bytes. They don't know that. So the
But they can look at
initiator,
the bytes and can figure out whether it matches with the v1 version.
yeah, so how so yeah, so supposing uh, yeah, so let's imagine cases. So supposing we send some bytes which are not magic bytes, like
Mm-hmm.
supposing the bytes received were a b c d.
Mm-hmm.
So these do not match the magic bytes.
Mm-hmm.
So the magic bytes are fixed. Okay, let me write like this. Okay, the magic bytes are red color. Okay, so
Right.
supposing that's 4 bytes also. So supposing this person gets some blue color thing. It just gets 1 byte of the blue color byte. So it knows for sure that it is not magic byte and it is talking in V2,
Right.
right? Like
Yes.
because it doesn't even the first byte doesn't even match the 4 bytes magic bytes, so it knows that it's talking in v2,
Makes
and it will
sense. Yeah.
immediately respond back with the with its alligator swift and garbage, because it knows that the other connection is talking in v2. And it's possible that sometimes instead of one So this is what happens most of the cases. But it's also possible that in some rare cases, maybe the first 2 bytes are the magic bytes and only the third byte mismatches. So,
Okay.
so when the responder gets the first 2 bytes, uh, it's still not sure whether it's talking on in V1 or V2.
Hmm.
Only when the third byte is received, it knows for sure. Like when the third byte is received, it knows there's a mismatch, and these 3 bytes don't match the magic byte, and it's talking in V2. So it has to wait for like 3 bytes.
What if the third byte also matches? Like in very rare case situation.
Yeah, in extreme rare cases, then it will have. So the BIP says that you can wait for up to 16 bytes, the 4 bytes
Uh,
network magic as well as this version thing. So that is the uh, like. Can you see my other screen? The V1 P2P message format.
yes, we can.
Yeah, so the V1 P2P message format has 4 bytes network magic and 12 bytes for the command. So the bytes are VERSION, that's 7 bytes, and then the
Right.
rest is all zeros.
Right.
So if it was V1, it would, so we wait for up to these 16 bytes to be sent. And if all these 16 bytes match, we know they're talking in V1 protocol.
Right. Makes sense. Yeah. So like, yeah, it
So
will watch up to 16 bytes, and if a mismatch happens, and then it will directly shoot its alligator shift instead of waiting for the full alligator shift to be received from the initiator.
yeah, exactly. But that's like
Okay.
really rare cases. Usually what happens is the first byte itself mismatches and they
Hmm.
directly show to the alligator shift.
Right. Right.
So, but yeah, but they talk about all this in the so that's the only difference between, that's why we have two different functions here for initiate V2 handshake and respond V2 handshake.
Makes sense. Okay.
Uh, so this will shoot only when, like, you can go through the code if you have time. Uh,
Mm-hmm.
this will shoot only when there is a mismatch happening from the V1 prefix.
Right.
Uh,
And this code checks up to the same 16 bytes. Yeah, there is a comment.
yeah, it
Return
checks
my.
up to 6.
Hmm. Okay. Okay, makes sense.
Then there's something called complete handshake and authenticate handshake. These are done by both of them, like both initiators and responders.
Right.
Uh, what complete handshake does is it calculates the ECDH secret, gets all the keys. Initialize V2 transport will initialize all the keys and the garbage terminators
Right.
and the session ID.
Right. So these are all the like key value pairs that is getting stored in
Yeah.
that. Hmm.
So it'll instantiate all of that, and then it will shoot out the garb. Wait, what? Oh yeah. So it has already sent garbage. So this will now send the garbage terminator
Mm-hmm.
and oh yeah, decoy packets if you want, and okay, the transport version. So message to send is what is being sent. So it's we are first storing the garbage terminator in it. Then we are also sending like 10 decoy packets simply for test framework.
Mm-hmm. Okay.
Uh, and then we are also sending the transport version.
So this is under
And
which class? Like it's in V2 P2P.py, and
yeah,
it.
it's called encrypted P2P state.
Okay.
So, so yeah, it just does this sending. So if you look in the BIP diagram, it does all this, making the CDH secret, initializing this, and also sending the terminator and the encrypted packets of the transport version.
Okay,
And this is
makes
like
sense.
also, yeah, it's also authenticating the data.
Hmm.
Garbage, yeah. And then finally, someone has to authenticate and make sure that all these garb, like all this stuff received by the other node decrypt correctly without any failures. So that is done by this function authenticate handshake. So it will just wait for data to be received, and once the garbage terminator is reached, it will yeah, like once a garbage terminator is received, you will know how long the garbage is, and you can authenticate the so this you need to wait for the entire garbage to be received so that this function
Right,
works correctly. So yeah, so
makes
this
sense.
ensures that received optional decoy packets transport version are authenticated, and this also marks the V2 handshake as complete finally. So that finishes the V2 handshake. Like why we kind of need separate functions for complete handshake and authenticate handshake is because complete handshake basically returns all these stuff, right? Garbage terminator, decoy packets, and the version packet, and you need to send it over the wire.
Right.
So to send it over the wire, you need to go back to P2P.py and go to this send message, send raw message. You need to go back to this function P2P.py to send it.
Right.
So that's why it's kept as two different functions.
Okay, so it's just creating the message to send and like creating the message byte with all the data.
Yeah.
And the authentication is it returning anything, the authenticate handshake?
Whether it's just successful or not, like if the authentication was successful and the length of whatever bytes is processed. Also, authenticate handshake needs to read data. And we saw in our last session how in P2P.py reading is done just by odd data. Like we can't say read the next 16 bytes of data. We can only get whatever was read on the socket using this callback whenever data is being read. So that's another reason why we have two different functions.
Makes sense. Okay.
So I have a question.
Yeah.
So what if like a Bitcoin node connects with let's say a non-Bitcoin node? It's not Bitcoin, just sending garbage. So it will think it's V2, and then when will it fail? Will it only fail at authenticate handshake, or will it fail earlier? Does the question make sense?
Yeah, in authenticate handshake, because like it's just sending garbage, right? So 4095 bytes will have to be crossed. So that logic is in authenticate handshake.
Okay, but still the node will send the alligator swift and stuff to the node. I mean that garbage server. Okay. Does that have an issue? Hello, can you hear me?
Your voice is robotic.
Hello.
Is it my
What about
connection?
now? Hello, can you hear me?
Hello. Oh yeah, I can.
Okay, yeah. So when it receives, okay. So the only thing that'll be wasted is basically the respond. No, it won't respond also, right? The complete handshake is not it.
Hello.
Hey, I can hear you.
Okay.
I can hear both of you.
What?
I'm going to stop talking. I think I understood the question. Basically, authenticate will fail. The others won't fail.
So Strat, can't you hear ML?
Like I can hear him, but he's in a like robotic voice, so I can't make out what he's saying.
Okay. So what he was saying is like when the like when something goes wrong in the protocol, if I understand his question correctly, when something goes wrong in the protocol, when will the function like raise error in the complete handshake or in the authenticate handshake?
Oh yeah, in the authenticate handshake, because complete handshake doesn't do any authentication. It just initializes all the keys. It doesn't decrypt
Hmm.
anything. Like there's
Right,
nothing being done.
right, right.
It's
Makes
authenticate
sense.
handshake which will read up to garbage,
Okay.
and if it crosses more
So
than the garbage length, it'll again fail.
so then the next question is like, is some kind of DOS attack possible to V2 things? If like I guess only if complete handshake is computationally intensive, then like garbage servers can keep sending this. No, but then yeah, the node will block the IP, right? Okay,
Yeah,
got it.
Yeah,
yeah,
if it keeps being.
yeah. I guess that makes sense.
Yeah, and ECDH is all not that computationally expensive.
Okay,
Like
Hmm.
it's expensive, but
okay.
the BIP says that uh, like it's a reasonable trade-off. Like even though this special kind of ECDH is slower than our normal ECDH, it's an acceptable trade-off because our connections usually last for days to weeks. Our P2P connections
Right,
with other nodes in the network.
right. Yeah.
It's still pretty fast.
But yeah, it's still gonna be like very difficult to DOS it with this because like the node has like all the banning mechanism and stuffs like that. So if somebody is misbehaving, they will block that connection and put it in a ban scorer. And so yeah. Okay, cool. So let's move ahead. Where exactly we are in our schedule of questions?
First one.
We just cover first one, but we talked about a lot of things. That's okay. We kind of like diverted into various topics. So let's try the second one. Um, we kind of covered why there are four different functions because different functions are doing different things. And yeah, and the second
Yeah,
one is
this is
like,
the for easy.
yeah, how are inbound connection modified to support V2?
However, in
See where the version message is sent
I think
and
that we
we,
covered as part of respond.
yeah, I guess so.
so, however, yeah, so yeah, we saw last time like inbound connections are made using add P2P connections, and
Hmm.
it calls this peer connect thing. Uh, this is in P2P interface peer connect. It will call the transport layer stuff,
Hmm.
P2P connection. And in an inbound connection, like, is there a visual somewhere? Have I drawn? Yeah, like this is an inbound connection, right? So the test node doesn't need to initiate the connection. So we are the P2P connection.
Hmm.
And in an inbound connection, the P2P connection has to initiate the connection,
Right.
right?
Yeah.
So that means if we are the initiator. If we are the initiator, we have to follow this sequence: initiate V2, complete V2, and authenticate handshake.
Right. But here in the case, like inbound
So,
will be the responder.
so this no, here inbound is the initiator.
Okay, maybe I'm confused. I was talking about something else. Okay, yeah, that makes sense. Like if we are the initiator, then these are the three functions that we cover. And if we are responder, then we start with respond v2 handshake. Okay.
Yeah. So so when we talk about inbound and outbound in this test framework, we only talk about inbound to test node. Like we always talk with reference to the test node, because test node is the actual Bitcoin process happening. We don't think about P2P connection.
Right. Yeah.
So so this means this is inbound to the test node. So P2P connection will have to send the alligator swift and garbage bytes.
Right.
So if you look in peer connect, how we've modified it is like if V2P2P support is enabled, you
you
set the
create
state
an
row, and
encrypted P2P
you
state.
also create
that structure.
an object of that, and and we say the initiating is true. That means we are the the P2P connection is the initiator.
Right.
So what that means is when a connection is made, and we are the initiator, we will immediately send the alligator swift and garbage bytes. So like if we support V2, we are the initiator. That means we are the inbound connection here.
Right.
And we haven't tried the V2 handshake yet. We will immediately send the L-swift and garbage bytes.
Makes sense.
So then the rest of the handshake is like, we are the initiator. We have sent everything. Now we have to wait for data to be received from the responder, right?
Right.
So any data that is received, you get it in on data. So this callback function, data received is actually where where you get data read from the socket. It will just append to the receive buffer, and normally it will just call this on data, which will say how you should read messages.
Okay.
Like, and it will like deconstruct the message. But now because we are on V2 and our handshake isn't complete, we will call this V2 handshake function. And here it will do calls to complete handshake and authenticate handshake.
Right. Okay. So this is like the mother function of like the V2 handshaking. Okay.
Yeah.
So it's calls complete on, then it's called authenticate handshake. Okay.
So I think this area of the code, this V2 handshake function, and also these handshake function, it's a good place to review. It's also some place where I'm looking for more reviewers. So anyone listening later to this call, or like if anyone wants to leave comments, feel free to leave.
Definitely.
Because I mean, so there are so many things being added. There are a lot of edge cases possible.
Right. Yeah. Yeah. It's a good potent place to like start delving into Bitcoin P2P test framework and all the fun stuffs together. Kind of like a nice intersection between Python, functional test, P2P. And so yeah, anybody is listening, like take a bite at it and ping Stratosphere in GitHub or in other places, and she will tell you what to do. Okay, cool.
Yeah, and then yeah, so this complete and authenticate handshake functions are done here. Initiate V2 handshake function happens in connection made.
Right.
Yeah, and then wait. Yeah, and where does the version message get sent? I think there's like a function here, connect send version. Yeah. Wait, what? Oh yeah, so peer connect send version will. Oh yeah, peer connect is what we use for inbound connections. And if you're sending version, it will make this call to peer connect send version. What peer connect send version does is it will construct the version message and store it in on connection send message. And on connection send message gets sent like in normal V1 connections, yeah, like on connection, like when the connection is made, normally on connect send message gets sent.
Mm-hmm.
That's normally what happens. But in V2, we don't do that. Like if that version message is set and it's being like you're asking to send it, what you do is you actually append it to this queue to be sent later.
Okay.
And then the version message gets sent after the V2 handshake is over.
Okay.
So at the
So-
end of complete handshake, we are sending some version, right?
Oh, that is the transport version. This is the version message.
Oh, okay, got it.
Oh,
Those are
okay, okay.
different.
This is the version message
And
of
the
the
transport
Bitcoin
version is
protocol.
empty. Yeah.
Okay.
So that is
That
same
makes
as the
sense.
old one, but transport
Yeah,
version.
yeah. Now I'm thinking if supposing you don't set this, like supposing there is no on connect send message being set because like we saw in peer connect there was a send version option set to false, right? Like it's like always they have apparently some options like if you look in peer connect, yeah, like only if the send version is being set they will call peer connect send version. Okay, and that means they will set on connection send message.
Right.
So I was just thinking what happens if we don't have this. Yeah, nothing happens. Yeah, we don't append anything, like it doesn't get sent. Yeah, everything else remains the same. Before and after. I mean, it doesn't affect the handshake at all in any ways. It just affects what are application layer messages being set after the handshake.
Right. Okay.
Yeah. And then this queue messages, whatever is appended here, it actually gets popped after the V2 handshake is done. So if tried V2 handshake is true, you send all these messages after V2 is done.
Makes sense.
So that's how inbound connections is modified to support V2. Outbound connections modified to support V2, kind of the same thing. Except in outbound connections, you use this respond V2, complete V2, and authenticate handshake. Right? So now the P2P connection is a responder. So it will respond back only when there is mismatch from V1 prefix.
Right.
And so that means you have to receive data first. You're not sending data first. So that's why everything starts from data received. You support V2, you haven't tried the handshake, you go to V2 handshake, and there all these functions get called. Respond V2 handshake, complete V2 handshake, and authenticate.
Right.
And then after that, all the application layer messages being.
Makes sense.
Then the next question.
Has the P2P
message size reduced, increased?
Reduced or increased in V2? Does order of sending P2P message matter in V1, V2, P2P? I guess I would say like it increased in V2 because now you're adding garbage and stuffs.
But garbage is not like
Oh,
by
like
message
that's
format. I meant
yeah.
this. Like
Okay,
this is
okay.
the V1 P2P.
This is the V2 message. Okay.
So I think there are just more handshake packets now, but the rest is the same. Is it? It's just encrypted.
No. There's slightly. Yeah, rest is encrypted, but those handshake packets are definitely more now. The packets are encrypted now, but because they're encrypted, they cannot follow the old message format standard. The old message format said that if there is contents here, you also have 4 bytes magic, command, payload checksum. So the total bytes would be 4 plus 12 plus 4 plus 4 plus the contents. That is what? 24
Right.
bytes plus the content.
Right.
Here
Here
it is
it's like
the
4,
length, the
16,
header,
20
and the
bytes.
marks.
So that's 20 bytes apart from the content.
Yeah, plus the content.
Okay, so actually it's reducing here.
So that's, yeah, slightly.
I guess the checksum isn't there. That's the difference, right?
Yeah, there's no checksum.
Because it's encrypted, and if it decrypts, that means it's valid.
I mean, like there is a Mac for that. I guess the Mac does the same thing, kinda, not exactly, but yeah, kind of like authenticating that you got the right
Mac is
data.
much more superior than the checksum.
Mm-hmm. Yeah.
Oh, okay.
Yeah, Mac is more, yeah, superior, secure kind of message
Right.
integrity check. Because
Right.
because checksum, like if there's a message and you calculate a checksum, you could change the message and you could calculate another checksum and you could send both of them, and the receiver would think nothing has happened.
Right. Okay. But
Yeah. Yeah. Okay.
Also, yeah, and this yeah, there is a small difference between this payload and contents, but it's just 1 byte difference. Like, should I go into it? It's just like they introduced something called message type ID for commonly used messages. Like these are all the most commonly gossiped messages. So before we just said payload, right? So now here the contents they have a
Message type.
1 byte or a 13 byte size, and then the payload. Yeah, the message type. So if it's a commonly used message like block, you won't write BLOCK and encrypt it. You will just use this message type ID and ID, which is 1 byte. So that gives a little bit of compression.
Right.
So
the
if
payload
you
is
use message
actually
type
smaller
ID too
than.
here, it's actually, yeah, but it's just like a 3 bytes difference, because this is 24 bytes, this is 16.3.1, and also 1 byte from message type ID. So just a 3 bytes less per message if you use message type ID.
Okay, cool. Let's move ahead. We are already at our 1 hour 10 minutes mark.
And the next question, does order of,
yeah, go ahead. Go ahead.
Does the order of sending P2P messages matter in V1, V2?
The order of sending the P2P messages after handshake we are talking about?
Yeah, after handshake.
So how good is the Mac? It depends. Does the Mac have like page number? No, I mean message number. You know.
I mean, like, why would the order matter in P2P messages? I didn't get the question.
Okay, like supposing I sent you a block message, and then I send you a get adder message, and you have to decrypt it in V2. But in V1, so I send you get adder and block, or I send you block and get adder in the wire. So in V1, like there's no problem whether which message I send first. But in V2, there's a problem if I send a different message first.
Why?
Because the key stream would change, and you wouldn't be able to decrypt it correctly. Yeah, exactly.
Oh, okay. I mean, like,
so Chacha20 uses the same stream, and then it keeps the remaining encrypted key stream there itself, and then uses it for the later on messages. So if the order changes, then we'll be using the different key stream, right?
Yeah, exactly.
Okay.
So you should decrypt it in whatever order I send it to you. So the order matters here.
Oh, okay. So I cannot just go ahead and decrypt the adder message first if the block message came before it. So I have to maintain that queue sequence.
Yeah.
Okay.
Yes.
In V1 it doesn't matter. Okay. Okay, makes sense. That
Yeah.
was interesting.
The next question. Why does false advertisement of services which a node can support happen? What happens if we start doing initial V2 handshake with a node which doesn't support encrypted transport protocol? How is backward compatibility maintained?
Okay, so why
I think
does
we
a
touched on
fall?
this last time.
Yeah, I guess we talked about it last time also. Yeah. Um, why does a false
Yeah.
advertisement of service which a node can support happen? So, false advertisement of services. We are talking about service messages, right? So that, or like you're talking about like, say the node is saying like I can do V2, but it actually can't do V2, those kind of situation.
Yeah, talking about that.
Okay. I mean, why would
So
the
they
node
could be
do that?
using, I guess, like custom branches of core, or maybe another implementation of core or something.
I can hear Emir only in robotic voice. I'm sorry. Raj, can you
Okay,
translate?
Okay, so he was saying like maybe that's because like they got a different branch of code. I don't see how that happens until like, but yeah, like I couldn't understand like why would somebody false advertise? What's the gain of false advertising here?
There's no gain, but firewalls could do it, or even during address
Okay.
relay, sometimes
Hmm.
it gets
And then it can
accidentally
get messed
stored,
up
or
basically.
someone could intentionally, yeah,
Hmm. What happens if we start doing initial V2 handshake with a node
so,
which doesn't support encrypted transport protocol? So if we start doing initial V2 transport for a node, I guess like it doesn't support, then it will disconnect. The receiving node will basically
yeah,
disconnect. Yeah. And
yeah,
then
it'll
maybe like the
disconnect.
sending node will understand that it does not understand V2, it will try again with V1 and then it will connect.
Yeah,
Right.
exactly. That's how
And
backward compatibility is
yeah,
maintained, right?
that's basically how backward compatibility is maintained.
And
Is like, so it will first try with V1 or like
yeah,
first ask for V2.
uh, it should first try with V2 and then go to V1
Hmm.
because
Yeah,
uh,
because
like
V1 is
if you
supported
try
by
in V2, it
everybody.
means pseudo-random byte stream, and then yeah, and also if you try in V2, it's pseudo-random byte stream, and then V1, it's uh, anyone can see what the messages are actually are. But if you try an upgradability path, like if you first start in V1 and then you try upgrading to V2, like if you talk in V1, anyone can read the messages and they'll know Bitcoin protocol is happening, and then it's pseudo-random byte stream. So it doesn't make sense to
Hmm. Yeah, yeah,
upgrade
yeah, yeah.
connections.
Right,
It
right,
makes sense
right.
to downgrade connections.
Yeah, yeah, yeah. That's true. Because like you are giving away that you are doing Bitcoin anyway at the first. Right.
Yeah,
Okay.
and yeah, and so that can be yeah, yeah, outbound connections. Yeah, so false advertisement of services you can test in the test framework. Like there's support added to test for that in
Mm-hmm.
outbound connections,
Right.
where like there is options to falsely advertise.
V2
There's like
support
an
for
option
the
set so that you can
interface.
falsely advertise the V2P2,
Hmm.
and then you can reconnect using V1.
Makes sense. Okay. Cool. We did cover all the questions. Nice. So,
Yeah.
any further question? Nothing from my side. Emil, you have anything?
No, nothing I can think of.
Cool. It's quite dense. It was quite dense, so but take
Am
a
I
bit
still?
of time. Yeah, yeah, I can hear you well. Yeah. Yeah,
Am
it's
I still a robot? That is what I was
No,
asking.
no, I can finally hear you.
okay. Yeah. So yeah, it was a dense one. It is a dense one. So people watching this stream, if you are a future Bitcoin Core contributor, you know what to study up now. So I hope like our explanation over here made at least some sense. So you can get started with it. And also like we provided a lot of details and basics on writing functional tests and exploring what are the cool things that you can do with functional tests. You can literally do a lot of stuff, so do check that out. And yeah, I guess like this is going to be a long forming project, and this is like a new thing that is happening in Bitcoin Core, so a lot of review, contributions, documentations, a lot of places to contribute. So do consider that. If that's your thing, leave us a comment. And if you have any questions, we'll be keeping an eye over there. Drop into our Discord channel to have like more in-depth Bitcoin Core related conversations. And yep, so let's call it a week here. Thank you, Stratosphere, for this amazing drawings and explanation. Thanks, Emil, for joining in, and we will see you guys in another review club next week.